Hello. Today we will be exploring the world of cryptography, and we're going to be focusing on the RSA algorithm. I'm Benjamin Bell, and I will be guiding you through the purpose, functionality, and implementation of this crucial cryptographic technique. So let's dive in. The RSA algorithm was named after its inventors Rivest, Shamir, and Edelman, and it is a cornerstone of modern cryptography. Its purpose extends beyond just encrypting and decrypting data. It plays a vital role in securing communication, digital signatures, and key exchange. Let's explore why RSA is so widely used. RSA finds its application in various domains, including secure data transmission, digital signatures, and facilitating the exchange of keys in secure communication. Its robustness stems from the difficulty of factoring large prime numbers. To understand RSA, we need to grasp some key concepts: public and private keys, prime number factorization, and modular arithmetic. These elements work together seamlessly to ensure secure communication. The heart of RSA lies in key generation. We start by selecting two large prime numbers, p and q, and then calculate n equal to p times q. The totient of n is crucial as it helps us choose a public exponent e. The private exponent d is computed using the extended Euclidean algorithm. Together these form the public and private keys. Now that we have our keys, let's look at how the encryption process unfolds. The ciphertext C is calculated by raising plaintext M to the power of the public exponent E and taking the result modulo N. This seemingly simple process is the foundation of securing our messages. Decrypting the ciphertext C back to the original message M involves using the private exponent d in a similar modular operation. This mathematical dance ensures that only the rightful recipient holding the private key can decipher the message. To better understand RSA, we need to acquaint ourselves with the Euclidean algorithm. This mathematical tool is crucial for finding the greatest common divisor, the GCD, of two integers. In the RSA algorithm, it plays a pivotal role in determining the modular inverse. Let's explore the Euclidean algorithm and its role in RSA. We'll do so when we look at the code. Modular exponentiation is the engine driving the RSA algorithm. It efficiently computes large exponentiations while keeping the numbers manageable. This function is applied in both encryption and decryption, making it a core component of RSA's strength and efficiency. RSA relies on the formidable challenge of factoring large composite numbers. This process makes it a robust choice for ensuring secure communication and enabling digital signatures. However, as we'll soon discuss, its efficiency does vary based on key length and computational factors. Now, let's look at the worst case scenarios for RSA. The efficiency of the algorithm is intricately tied to the factorization of large semi-prime numbers, and this process exhibits an exponential time complexity, denoted as O of 2 to the n power. While increasing key length enhances security, it also introduces potential impacts on performance. On the other hand, the best case scenario paints a different picture. When dealing with smaller prime numbers during key generation, encryption, and decryption, RSA demonstrates polynomial time complexity, or O of n to the k power. This characteristic allows for quicker operations, and the practicality of this scenario hinges on the specifics of the use case and the sizes of the prime numbers involved. Choosing an appropriate key length is a crucial decision. Longer keys offer heightened security, but they may demand more computational resources, potentially impacting performance. Striking the right balance between security and performance is key, especially when tailoring the algorithm to meet the specific requirements of a system. In exploring the key factors influencing performance, we examine the impact of key length, the availability of computational resources, and considerations for applications with real-time requirements. These factors play a pivotal role in determining how efficiently RSA operates in various scenarios. To conclude, the performance of the RSA algorithm is intimately connected to key length, computational resources, and real-time requirements. As we've seen, understanding these factors, coupled with the insights from Big O notation, is fundamental for effective implementation in diverse applications. Now that we've just explored the theory behind RSA, we'll be taking a closer look at the code implementation. We have C# code that includes functions for the Euclidean algorithm, modular exponentiation, and key generation. We'll walk through each function and understand how they contribute to the overall RSA algorithm. In conclusion, the RSA algorithm stands as a guardian of sorts for secure communication. Its significance spans from encrypting sensitive data to facilitating secure key exchange. Understanding its inner workings enhances our appreciation for this very robust cryptographic method. It really underpins our digital world. Now let's dive into the code implementation of the RSA algorithm. This C# code, encapsulated in the algorithm lib namespace, provides a practical realization of the RSA algorithm. You can follow along with me as we walk through the main components. Firstly, we have the Euclidean algorithm, here called Euclid. This algorithm efficiently calculates the greatest common divisor, the GCD, of two integers. In our context, it's used to find the modular inverse later in the code. Next up is the modular exponentiation method. This is a crucial function that efficiently computes x to the y power divided by modulo n, using the square and multiply technique. This operation is fundamental for both encryption and decryption processes. Moving on, we have the generate private key method here. This is responsible for computing the private key called D using the extended Euclidean algorithm. This ensures a positive value for D. Now let's examine the encryption processes within the encrypt method here. This function utilizes modular exponentiation to encrypt a given plaintext value, which in this case is called value, using the public exponent e and modulus n. Lastly, we have the decrypt method, responsible for decrypting a given ciphertext called value. It also uses modular exponentiation, this time with the private exponent d and modulus n. Together, this code here allows you to take plain text, encrypt it using the RSA algorithm, and also decrypt it using the RSA algorithm. So, as we can see here, we have a series of tests with one for the RSA test. So this test has various values that we will use to implement in our RSA algorithm. As we can see, it's a fairly simple test. It will take various values, plug it into the function, and then if our algorithm is working correctly, it will be able to encrypt and decrypt those values properly. So, as we can see, when we run this unit test, we successfully pass this test, which means our RSA test is successfully implemented. This is a very simple version of the RSA test. You can get very much more complicated with it, but at its base, this is the fundamental algorithm and method for RSA, which, as said before, underpins the security of our digital world. It's a very important algorithm and one that I hope I helped you to better understand. Thank you for your time. This is Benjamin Bell.